Okay, very nice. Then I welcome Carla Cederbaum from Tübingen in Germany today. And she's going to talk about the uniqueness result for an overdetermined system of PDEs subject to overdetermining boundary conditions. That's a long title. Thank you, Carla. Go ahead.
Thank you, Julian, and thanks to Matteo for the invitation. And I'll complete the title by saying that these PDEs that I'll be talking about are arising in the context of the static black hole uniqueness theorem in general relativity. And I agree, it's a very long title. Thanks for coming, and please feel free to interrupt me anytime if you have a question, because I'll start it out with geometry, and I'm aware this is a PDE and analysis seminar, so I'll try to run you through most of the important aspects of the geometry setup that I'll work in. So here's the setup. We're working in an n-dimensional Riemannian manifold, which is smooth. And n is going to be at least 3. And we're going to see an important example in a minute, but for now, any Riemannian manifold will do. And one major thing I'm assuming about this Riemannian manifold is that the scalar curvature, which I'll denote by R index G, is going to be non-negative. There are physical reasons to assume that, but for now, let's just take it as a geometry problem. And if you want, you can rewrite this as a second order nonlinear PDE of elliptic type. If you write this out in coordinates that you choose on this manifold. So I'm thinking of this, oh, it's not a PDE, but it's a PD inequality. PD inequality. Okay, so that's the PD inequality I have in mind here. And in addition, I have a second, now really PDE, namely the harmonic equation for a function u on this manifold, where u lives on this manifold and goes to R. And really, most of the time, I'm going to assume that this function is positive. And this, again, of course, is a second order PDE in this case, but it's actually linear, as you can see. So this is going to be a harmonic function I want to have living on this manifold. And of course, I could always just solve the harmonic equation if I prescribed adequate boundary conditions, but as all of this is about boundary conditions, I'll not do so yet. Then I'll first run you through more details about the manifold that I'm going to assume. So here is a picture. Let's see, I have a surface sigma 1 here and a surface sigma 2 here, and maybe a different type of surface sigma 3 here. And what my manifold now looks like, so this is M, is it has a boundary. M has boundary, which is non-empty, and consists of a union, a finite union of compact boundary component. So the boundary should consist of a finite union of compact boundary components. And of course, these boundary components are all n-1 dimensional manifolds. Okay? And they're compact. Well, let's make them compact. Okay. And on the other side, M outside some ball, or outside some compact set, rather. So here, M outside some compact set, I'm going to call that E. That's another n-dimensional manifold, just the part outside this orange cutoff. And I'm going to assume that this Mn outside some compact set, which I call E, is diffeomorphic to Rn outside some closed ball. Okay, So my manifold has some bulk interior, which can have very complicated topological structure, differentiable structure, and everything. But it has an inner boundary consisting of only compact, finitely many compact components, and an outer E, which we call N. That's where the letter E comes from, which is nothing else but really Rn minus a closed ball, so an exterior region of a ball. And we're going to suppress the diffeomorphism. We're just going to pretend that outside some compact set, the manifold is nothing else but Rn minus a closed ball. So this is how this manifold allows to pose a boundary value problem both for the metric G that we don't know in advance, for the Riemannian metric on this manifold, and for this function u, which is going to be harmonic with respect to the metric G that we don't know. Okay, and if I say boundary values, I mean boundary values both at each of the components of the inner boundary, and which are the compact ones, and the what we call the boundary at infinity, or the asymptotic boundary, which is the direction of the radius going to infinity in my Rn. So I'm going to draw that in here. So we have some radial coordinate on this, which this is diffeomorphic to Rn minus a ball. And because this is just Rn minus a ball, I have a radial coordinate, which for various reasons I'm not calling R, but S. And it goes to infinity as we go out along the manifold, and goes to some finite value as we approach this orange cutoff. And now in this setting, I can write down the variables for which the boundary value problem will be worded. So to make this into a boundary value problem, I will assume that that the metric G extends smoothly to the boundary. So the inner boundary, which was this union of finitely many components. And I will call the induced metric on those sigma, and the extrinsic curvature, or second fundamental form, whichever name you prefer, I will call H. And if you've ever heard about mean curvature, then mean curvature is the trace of this, and will be denoted by a capital H, and that's the trace with respect to sigma of H. So each of these boundary components now has a Riemannian metric on its own, and the second fundamental form and mean curvature inside the higher dimensional manifold. And if I want to prescribe boundary values at the inner boundary of the manifold, I will prescribe values for sigma, maybe, or properties of sigma of the induced metric, and I can prescribe values for the mean curvature and properties of the full second fundamental form to get a boundary condition at the interior. And we would typically view conditions on sigma as some kind of Dirichlet boundary conditions, because it's just the induced metric, and conditions on the mean curvature or the second fundamental form as some kind of Neumann derivative, because the extrinsic curvature plays the role of some normal derivative in some sense, if you want. And for the function u that we have here, we also want that u extends smoothly to the boundary. And of course, the value of u on this boundary will be a Dirichlet boundary condition. And also we want to look at the normal derivative of u, which I'm going to denote by nu of u. And of course, prescribing that would be a Neumann boundary condition. And before I go on, I should tell you which normal I'm referring to, because that can be confusing as well. So let's go back to this picture. So I will always talk about the normal as going into the big manifold from the boundary into the interior, not to the exterior, which you may be used to if you look at normal value problems. boundary value problems in normal direction usually. Okay, so if you have those in mind, keep in mind that we use these. And the reason why we use these is that these point towards this infinity in the orange region. And therefore, I will even call that one the outward unit normal, even though it goes into the manifold, because it goes out to infinity. And coming from general relativity, the infinity is where the observer sits, and that's why the normal points outwards towards the observer. So there's really a reason. So this is the outward normal, and this leads to mistakes in some papers and misunderstandings between PDE and geometry people. So that's why I'm stressing it so much. Outward unit normal. Okay, so that for the inner boundary, and for the other boundary, for the boundary which I get for S going to infinity, so the boundary at infinity, and recall S was the radial variable in Rn without the closed bar. For that, I'm also going to impose boundary conditions. And if you've ever heard somebody talk about asymptotically flat Riemannian manifolds, then this is a special instance of such an asymptotic flatness condition, but it's much stronger than the one you might have seen before. So I prescribe the asymptotics. And I want that the function looks like 1 minus some constant mu over s to the power n minus 2, and n was the dimension here, and we are at least 3, so this is at least 1, plus terms that decay of the order 1 on s n minus 1, and this is as s goes to infinity, and mu is in R, and is called a mass parameter. Okay, so if you don't know, if you're not familiar with the O notation with the little index, this means that I can take 2 derivatives of u and 2 derivatives of 1 minus mu over s to the power n minus 2, and then the term will, the error term will decay as good as 1 over s n minus 1 taken the according number of derivatives. So it's an error estimate, and you can word it in weighted Sobolev spaces if you want, but I wanted to make it very clear here what are the orders of things. But in the actual theorems, these O notations are replaced by weighted Sobolev spaces. So this is what I want for the function, and you can think of it as harmonically asymptotic, asymptotically harmonic. Sorry, and then the metric you want to look asymptotically. You want it to look like the following: 1 plus 2 m over s to the n minus 2 delta ij plus a similar term. Where delta ij are the components of the Euclidean metric in Cartesian coordinates, so, or the Kronecker delta, whatever you prefer to call it, and m and r is another mass parameter. And these conditions are called asymptotic isotropy conditions. So what do they really, why are they called asymptotic isotropy conditions? Well, because they are saying that at the first order term after the 1 or the delta ij in the metric, everything is really isotropic in the sense of being spherically symmetric. Okay, so it's really asymptotically isotropic, and the lower order terms that are coming after that, they don't need to be isotropic of any kind. They can have angular dependencies, but the highest order, the first term after the 1 or the delta ij are isotropic. Okay, so now after seeing these asymptotic isotropy conditions, let's write down an example where all these things are going to be important. And this is the Schwarzschild manifold. Oh, I forgot to say one thing, just a moment. If we look at them again, and we're thinking of them in the spirit as a Dirichlet and Neumann condition, then somehow prescribing that the function goes to 1 and the metric goes to delta ij at the highest order can be thought of as a Dirichlet condition at infinity, while the next order, and the fact that we ask that derivatives of these errors also behave accordingly, can be interpreted as some kind of Neumann condition. So these are mixed Dirichlet and Neumann, or not even mixed, but both Dirichlet and Neumann conditions at infinity simultaneously already. So let's go now to the example of the Schwarzschild manifold. And the Schwarzschild manifold is a metric with the parameter m that has the form 1 minus 2m over r to the n minus 2 dr squared plus r squared d omega squared on rm infinity cross Sn minus 1, where the r variable is now a radius variable, and it's the reason why I called the other radius s before, because it's not the same thing. And this here is the canonical round metric on Sn minus 1. And m in r is again a parameter, which is again called the mass. And this, of course, is our manifold M. So this is an example of a Riemannian manifold. It's the very most important example for this talk. So I want to spend quite some time on giving you more insights about this example. So first of all, we see that it's, of course, spherically symmetric, because all the coefficients of the metric depend only on this radial variable r. Then one more important thing to know, so it's spherically symmetric. Let me write this down. It's actually asymptotically isotropic of mass m, which is why I gave the same name m to the parameter involved as r goes to infinity, which means that you can rewrite it in a different way in terms of an s coordinate in which it will be asymptotically isotropic according to the definition I gave before. So upon a coordinate change, moreover, it has zero scalar curvature, so it in particular solves the partial differential inequality I wrote down earlier. And this is just computation. And of course, it carries a function um, and the function um is the square root of 1 minus 2m over r to the n minus 2. And this function,
sorry,
yes?
Your Rm is such that that term blows up, the denominator blows up.
That's a very good question.
Is that like the event horizon or something like that?
Yes, exactly. So the Rm, if the mass is positive, and I'll talk about this more in a second, if the mass is, the parameter m is positive, then the Rm is the root of the denominator, and is exactly, then the Schwarzschild manifold describes the t equals 0 slice in a black hole spacetime, and Rm is the position of the black hole horizon at this point of time. If the mass m is 0, if you look at the formula for the metric, this is just the Euclidean metric in spherical polar coordinates, so it's not very surprising. And then I can use the Rm as 0, because the Euclidean metric, of course, in polars extends all the way down to the horizon except the horizon. And if the mass is negative, then the function in the denominator here will not have any zeros. And that's called the naked singularity version of the negative mass Schwarzschild is a naked singularity. It has some kind of bad asymptotics only as r goes to 0. And then Rm will also be 0. Yeah, so that's why there's this Rm. I'll say more in a second. So this function here, um of r, is the same function that's in the denominator here. But the square root out of that is called the lapse function. And it is indeed solve the harmonic equation on all of the manifold. Okay. So we have now a scalar flat, so 0 scalar curvature metric example, which with a harmonic function living on it. And I'll write down what I just said. If m is positive, this models a black hole, a static, spherically symmetric black hole. with black hole horizon at r equals 2m to the power 1 over n minus 2. And if m is 0, this is just Euclidean space in disguise in polar coordinates. And if m is negative, then this is a naked singularity. In both cases, we have that Rm can be chosen as 0. Okay, so from now on, we're going to only be interested in the positive mass case. And then in that case, if you look at the metric, and I said this briefly before, if you look at this coefficient, of course, at this number, the number is chosen exactly such that this coefficient, the denominator becomes 0, so the coefficient blows up. And this is where the black hole is located. And it looks maybe surprising to you, but there's a coordinate change that you can perform in the radial coordinate, so respecting the spherical symmetry, which allows you to extend this metric smoothly across this 0 of the denominator of this function. Okay, so there's a coordinate change. S is S of R, such that GM in S coordinate can be smoothly extended to Rm cross Sn minus 1 and beyond. And I'll give you more details about this later.
So may I ask just in between?
Sure.
So this means actually that the black hole belongs to the universe and it's not a singularity of the universe. Is that
Yes.
what it's saying? Okay.
Yes. Although this is only at time 0, right? This is the Riemannian section of the space-time.
Right.
So and in this S coordinate, actually, this Riemannian section can be made to be geodesically complete. Mm-hmm. Okay, I'll draw a picture in a second, then it will hopefully become more clear. But first, I want to say that it can be smoothly extended. So in particular, we will have an induced metric sigma, as I started with in the abstract setting, not this example, which will actually be round because of the spherical symmetry. And it will look like, sorry, Rm squared d omega squared. So it will be completely spherically symmetric, completely round, and its radius will be this radius Rm, where we cut everything off, where the horizon is, this value. You don't need to remember the precise value. And it will have actually vanishing second fundamental form. So in particular, it will be a minimal surface. So if you've ever heard the talk about mathematical relativity, they probably used the definition of a minimal surface as mimicking a black hole horizon. And here you have an example now of this phenomenon. And also up in this very same coordinate change, as S goes to infinity, both UM and GM are asymptotically isotropic. With mass M. So they satisfy the condition asymptotically that I wrote down. And in the condition, I had a different parameter for M, for the function and for the metric. But here they satisfy these asymptotics both for the same parameter, namely for this mass M of this black hole. M is referred to as the mass of the black hole for physics reasons. And then there's another PDE that they satisfy. We have the following PDE. We have UM times the Ricci curvature of GM. It's a more complicated curvature object, is equal to the Hessian of UM. So that's another second order nonlinear system of PDEs. Okay, and it's overdetermined, highly overdetermined. And has very few solutions, as we will see. Okay, so before I continue stating any theorems, let me draw a sketch of the Schwarzschild. The best sketch to draw is this, where you should imagine all of these as being rotated. So it's completely spherically symmetric, and this is called, well, this is a not very pretty version of Flam's paraboloid. So it's a very, very good sketch of Schwarzschild once you suppress enough angles, because it's actually this way, the geometry, the intrinsic geometry of the Riemannian metric embeds isometrically into Rn one dimension higher this way. So the intrinsic geometry of this sketch is absolutely correct, as according to the, for as long as you forget that I drew it a little bit weird there. Let's see. Okay, now it's better. And you see down here, you have this minimal surface, which is the boundary, and which had also the second fundamental form vanished. And up here, you have S to infinity, which corresponds also to R to infinity in this other coordinate there. And the fact that the boundary is minimal or has second fundamental form vanishing, you can see in that the profile, the radial profile, goes down vertically at this point. Yeah, so this is in R coordinates. And now what one can do, and what happens when one uses this S coordinate, is that one can actually double this manifold by reflection. So just take another copy and glue it to it. And then it's smooth here. And the way this is done is completely explicit. I'll not go into details now, but then S here is some value Sm, which one can compute and depends on the dimension. And here you have S going to 0. So you actually, then this original Schwarzschild manifold that I wrote down for you, the blue part, can be extended not only to the boundary, but actually across the boundary to a second copy of it completely smoothly. And this whole thing is geodesically complete. Okay, I hope this answers Julian's question. Okay, so what do we know, and why do I run through this example so carefully? There's a classic theorem from the 1980s at the latest. There were previous versions with extra conditions, and the final version is due to Bunting and Masoudul Alam. Of the following static vacuum black hole uniqueness theorem. Which says that, okay, you are given a three-dimensional Riemannian manifold as before, with boundary consisting, of a finite union of compact components. And Gij should be asymptotically isotropic of some mass m bigger than 0. And you have a function, or G, and you have a function U from M to R, U positive, such that Laplacian G of U is 0. And U is asymptotically isotropic of the same mass. And at the inner boundary, you want that the mean curvature is 0 at each component, the function is 0 for each component. So it's a minimal surface, and this function u is 0 there. And you have the following PDE. You have u times Ricci g is the Hessian g of u, and scalar curvature is 0. Then you can conclude that G is isometric to Schwarzschild of this very same mass m. And moreover, the function u coincides with with the Leb's function of the Schwarzschild example. So this says that provided you have these asymptotic conditions and the function and the metric have the same mass asymptotically in this isotropic expansion, which is positive, and provided the inner boundary is a minimal surface and the u has 0 Dirichlet boundary values on the inner boundary everywhere, provided that the function is harmonic, the scalar curvature is 0, and the Ricci obeys this PDE here, this highly overdetermined PDE, as I told you, then everything is just the example we saw before. So that's not too surprising. That is very surprising, and it can be interpreted physically as saying the only black hole, h equals 0 and u equals 0, is interpreted as to be a static black hole, which satisfies this equation, which comes from the vacuum Einstein equations, for those of you who know what that means. So it models vacuum. The only such black hole which is isolated, meaning it satisfies the asymptotic conditions, is actually Schwarzschild. That's why it's called a uniqueness theorem for static vacuum black holes. Okay, so that's what the theorem is. The old theorem, and it was of course proved under extra conditions way before and also afterwards with additional different methods, but this is the only result I'm aware of that proves this full generality uniqueness statement. So the first question, maybe you're asking yourself, why is she talking now about a 3-dimensional result when in the beginning she mentioned n-dimensional setting? So what about higher dimensions of this result? And one answer I can give to you is that there's a result by Gibbons, Ida, and Shiromitsu from 2002, which generalizes this very result to higher dimensions, and we don't need to change anything about the wording. All the statement will remain the same, but there's a small gap in the proof where something isn't argued very carefully. And I'll maybe mention that later again. You may also wonder, why didn't I just write down this boundary condition on the inner boundary in the beginning, and why didn't I mention this condition in the beginning, and why did I allow, instead of just scalar flat metrics, non-negative scalar curvature? And the answer is given, maybe if I write down my theorem, which reads as follows. And it's a little bit tedious to write it down, so I'll try to abbreviate some things. Be asymptotically isotropic, mass m, non-negative scalar curvature, and let u from m to r, u bigger than 0, be asymptotically isotropic of the same mass. And be harmonic. And let partial m be a disjoint union of finitely many boundary components which are compact. Then I assume the following: on each sigma I, and n bigger than or equal to 3, of course. On each sigma I have either that the second fundamental form vanishes, and hence in particular the surface is minimal, And in that case, I also want the function u to be 0, and I want the normal derivative of u to be non-zero and constant. And I also want the scalar curvature of the boundary to be constant and positive. So that's the scalar curvature of sigma I. Or I want that h is a positive constant. The trace-free part of the second fundamental form vanishes. We're going to call this umbilic. U is constant. The normal derivative of u is constant and positive. And we have some mysterious conditions that I can never remember precisely. Namely that the scalar curvature of the boundary is constant. And now are the spurious conditions. There exists a constant that can depend on the number of the boundary component, which is bigger than a dimensional constant n-2 over n-1, such that the scalar curvature of the boundary is related to the mean curvature like this. Scalar curvature is ci times the mean curvature squared, and 2 times the normal derivative of the function is ci minus this threshold that I imposed times hi times ui. Okay, and in this scenario, then everything is isometric to Schwarzschild. And the mass is necessarily positive. I didn't assume that. So let me first, before I give you any ideas about the proof, let me first run you through the difference between the theorems, the traditional one and the new one. So the first difference, of course, is the dimension. I allow arbitrary dimension. And then the next difference is that I'm not assuming the PDE. So the PDE that's here, and also the PDE that here in the old theorem by Banting and Massoud-Lam about static black hole uniqueness, they all disappear and get replaced by the non-negativity of the scalar curvature condition. So before we had a highly overdetermined system of nonlinear PDEs, and now while keeping this harmonic PDE, of course, we replace this overdetermined system of PDEs by just one inequality, which is a partial differential inequality, okay, which is of course highly underdetermined. And if you ignore the possibilities in the or case, then in the either case, we are exactly in the same scenario as Banting Massoud-Lam is, except that I wrote this and not just the minimal surface condition. I did write this, the non-zero-ness of the normal derivative, and I required that the scalar curvature be constant on the boundary component. However, if you assume the full so-called static equations, namely this equation here with the Hessian, and not just the inequality that I'm assuming, then all of these follow actually, yeah? All these follow from U Ricci G. Okay, so if I did assume that this full static equations in higher dimensions, for example, or in lower dimensions, then all the things I circled, so all the things I ask in the either case are implied automatically by the setup in Banting Massoud-Lam. So I'm putting more boundary values conditions that are automatic in the case I use the overdetermined PDE. But now if I have only the weak underdetermined partial differential inequality, they are extra boundary conditions that I have to put. Plus, I'm allowed to include this or case where I have positive mean curvature and other conditions, okay? And the details of these conditions is not so important. So maybe before I say anything about the proof, let me say, what does the or case mean? So what does it mean? If I look at Euclidean round spheres, so just round spheres in Euclidean space, then they will all have positive mean curvature, which is constant. They will all be umbilic, so the second fundamental form will be pure trace. The function u in the Euclidean case is the function 1, so it will be a positive constant, namely 1 on each of them. The normal derivatives of all of them will be 0, of the function will be 0, because the function is 1 everywhere. So this is not valid in Euclidean space. And the scalar curvature of each of the round spheres in Euclidean space will be a constant. And now if you relate all these constants by these two equations here, then you will find that these equations hold true always if I pick C exactly the threshold n-2/n-1, which I don't allow here because I don't want to be in the Euclidean case, right? But if I pick C this threshold, then these conditions are exactly conditions satisfied by the mean curvature, the scalar curvature, and the function 1 in Euclidean space. If instead I look at my Schwarzschild example and I pick any sphere of symmetry here in my Schwarzschild example, then it will have positive mean curvature, it will be umbilic, it will have constant positive scalar curvature. The function u that I wrote down for you will be constant and positive on it by spherical symmetry, and the normal derivative of u as well. And it turns out that actually both these conditions are automatically satisfied for some constant ci bigger than n-2/n-1 on each of these possible green spheres, with C becoming asymptotic to the threshold n-2/n-1 as I go out to infinity, where everything is more and more close to Euclidean space, and C becoming more and more infinite as I walk down all the way to the black hole horizon. So in this picture, if I go closer and closer to this surface. And if instead I looked at negative mass Schwarzschild, then I would be under this threshold. So this condition is somehow saying a priori you can embed with your first derivative, with the Neumann condition, into Schwarzschild of positive mass. Okay, that's what this condition means. So embeddable with Neumann, with first derivative condition. Into Schwarzschild of positive mass. Okay, so let me use the remaining very few minutes to give you a very, very brief idea of the sketch of the proof in pictures. And the proof uses very few PDE methods, so it's maybe not so relevant for you anyway. So the idea is this: take your manifold, which has some infinity here and some inner boundary components. This may be a minimal boundary component, and this may be a boundary component with positive mean curvature. Then for each of the boundary components with positive mean curvature, I glue in a specific tailor-made manifold, which itself has a minimal surface down here and satisfies non-negative scalar curvature and has a function u living on it that satisfies the harmonic equation, so that the gluing here is C11. And then I do what the picture suggests, which is an original idea by Banting and Masoudul Alam. I double the resulting manifold. Okay, so now I have two copies and I glue them together. And this doubling, just as in the original proof by Banting and Masoudul Alam, is also a C11 doubling. And now, oops, sorry, don't know what I did now. Now I perform a conformal change, a well-controlled conformal change. Which allows me to get something which is still non-negative scalar curvature, still asymptotically isotropic, but this time of mass 0, and is geodesically complete. And this is the case of the famous positive mass theorem of Shane and Yao, now available in higher dimensions, I think from 18. Together with a low regularity version of its rigidity case by McFerrin and Shekel-Lahidi using Ricci flow from, I believe, 17, if I don't err. And this tells you that the new one, the conformally changed one, manifold, is actually Euclidean space. And then there's a clever strategy to work backwards and see that you must have started with Schwarzschild. And this strategy is what I contributed and uses detailed properties of harmonic functions on Rn, Euclidean Rn, and some topology results. So thanks there.
Thank you, Carla, very much. Are there any questions? Okay, so maybe I can ask a question. So your boundary value problem was overdetermined at the boundary, right? You had Dirichlet and Neumann condition on the boundary components. So this reminds me of Serene's theorem, because actually your normal derivative is constant. Is there any approach via Serene's result, that because he also concludes the symmetry of the domain if you have a Dirichlet and constant Neumann condition?
That's a very good question. I've been asked this question before, and unfortunately the answer is still I don't know, but I'd be really interested in looking at that in more detail. Yeah, I don't know if his result can be applied directly, or maybe you still need the glue-in technique.
Yeah, well, it's still non-compact to the domain, right? So
yes.
I don't think
Yeah.
definitely not be directly applied, but maybe there's a way to.
Maybe there's a way to transform it. Yeah, maybe the conformal change gives you enough inversion to be on a compact domain, or a suitably compact domain. Yeah, that would be interesting.
Okay, thank you. Any further questions?
Maybe I'll just ask something then. So usually when people look at the non-static problem, they are interested in the wave equation, right? So how do harmonic functions relate to solutions of the wave equation? Because so I would think of a harmonic function as a static solution of a heat equation, right? So how do you relate to the wave equation then?
Oh, I guess formally you could do in the same way as you mentioned for the heat equation, right? I'm not sure if this has any relevance though. So when people look at wave equations, they have maybe two things in mind that I can think of right now. So one is to study dynamical stability of initial data. So you prescribe initial data, say close to those of Schwarzschild, and then you want to evolve them, and that's the Einstein evolution equation, which is highly nonlinear, but a wave equation is a good toy model for that. So that would be one thing. But then if you perturb these initial data, if you think of my metric as your initial data and you perturb it, then I don't think this function U will survive, because it has so overdetermined boundary values that I don't see how they could survive through perturbation arguments, right? And the other question that I know of that will bring in wave equations would be to study waves on a Schwarzschild background for a different motivation than the one I just mentioned. And then I wouldn't see how knowing that manifolds of this type are Schwarzschild would impact those studies, right? But if you're looking at exactly Schwarzschild, then of course the function the static Lebesgue function is extremely important to understand the waves, because somehow if you look at the space-time, then what the tells you is the length of the dt killing vector field in the space-time. That's why it's called the Lebesgue. Okay, so if you think of the Schwarzschild space-time and you write it down, maybe I'll actually just write it down. So if you look at the space-time, and this you can do generically in the setup I'm using, if you write minus u squared dt squared plus a Riemannian metric, then this is called a standard static space-time. And if u is independent of t, and recall that my u was just defined on some m, and this is also a metric on m, then this is on r cross m, where t lives here. And this is called a standard static spacetime. And the u is called the lapse. And then really the dt is a killing vector field for the spacetime, and u is the length of this killing vector field. That's where the u comes from. Okay, so in that sense, it's related to the geometry of the space-time, not just in the Schwarzschild example, but in this whole class of spaces that I'm looking at. And so a wave on a manifold on a space-time that has this form will, of course, know about this Lebesgue function and need to know about this Lebesgue function very precisely. I'm not sure if that goes in the direction of your question.
Thanks.
Okay, anything else? Any further questions, comments? Okay, it doesn't seem to be the case, and let's thank Carla again for this nice talk.